Okay, we're going to look at pump head capacity relationship where we have a pump characteristic curve that's given right here, where we have the available head by our pump is a function of these constants time and q squared. This is basically like the velocity squared term, only it's been turned into a q squared term. And this sort of gives you the performance of your pump, how much head do you get when you're operating at different flow rates. So we want to see how this characteristic curve will fit with our system. Our system looks like this, and it has a difference in reservoirs of 50 feet, Z1 and Z2, and may not look like it, but that pump length is supposed to be about 600 feet, and it's 4 inches in diameter, and F is 0.02. So we know how to do all that stuff, so they're just kind of giving us the friction factor, and we don't have to do the Moody thing. So what is Q in this? So we can't just jump into here and plug in and get Q because we don't know what the available head is right now, or what the pump head is giving. So we need to, and oh, by the way, neglect minor head losses. We're not going to worry about those in this type of problem. So again, as usual, we turn to Bernoulli. We can go between points 1 and 2, and pressure at 1 is 0. Velocity at 1 is 0. Z1 is what it is. The head that's given by the pump is really what we're looking for here. P2 is 0. V2 is 0. Z2 is what it is. And then we've got the major head loss. But we don't have to go to Moody because they gave us the friction factor. So we're going to figure out a similar looking curve called the system curve, where we're going to solve for the head given by the pump by putting in all this other geometrical information. The only thing we don't really know is v squared, and so we end up with a curve that looks a little bit like this given curve. But remember, that's for head available, and that's kind of coming out of the box with our pump. This is our system. So what we want to do is change that V2 into a Q by taking V2 is equal to Q over A. So Q is equal to A times V2. So if we plug that in, we'll end up with an expression where, well, it says that that V2 is equal to 0.0255 Q. So we can plug that 0.050255 Q in for V squared. That's what we've done here. And we get a curve that looks a lot like the curve we had before, with just different numbers in it. So in order to find Q, it has to satisfy both of the system curve here, that's for our system, and the pump characteristic curve here, which is up HA. In other words, HA has to be equal to HP, so the available head is the same as the pumping head, and that's kind of obvious, but here it is. And if we solve that, it's not quite that easy. Yeah, that's pretty easy. You just solve it algebraically, and we take the square root of Q, and we'll see that Q is operating at 366 gallons per minute. So essentially, we found the intersection of these two graphs, the system curve, which is what our system is, and the pump curve or performance curve, which is what's coming out of the box.